for you. Upstairs?
Okay. Sounds like the mic's on. The screen is not on yet.
Shall we wait?
Do we need to switch to VGA? Oh, here we are.
Okay. So we have Joe Britton, who's going to demystify the type inference. Thanks a lot.
Thank you. Thanks, Marco. Hello, everyone. Buongiorno, Italia. It's good to see so many people here. I think historically, the Mediterranean countries in Europe have been a bit quiet in the Scala community, and I'm really happy to see that there's so many people here today, and hopefully it's the start of lots more activity in Scala from Italy and beyond. So yeah, good to see you all. Are you having a good conference so far? Good. This is going to be an interactive talk, so if you have any questions while I'm talking, or if I say something that isn't clear, shout out, tell me, put your hand up. Don't even put your hand up, just shout out, tell me. I'm going to be talking about, the title of the talk is Demystifying Type Inference. Type inference is a very complicated topic, and I've used this picture of a human brain to try and represent, as a metaphor for the type inference engine inside the Scala compiler. Because we don't really know exactly how it works. We can sort of prod it in different ways. We can attempt things, try them out, but there's no clear spec apart from the compiler itself. And we can learn about it. We can attempt things, but we can't easily know with certainty exactly how everything internally works. And there are many corner cases and many things that aren't as well understood as they could be. At the end of the talk, I will not have demystified type inference. I'm sorry. I might have made a few things easier. I might show you a few tricks. But if anybody comes away from this talk and understands or feels like you understand type inference, then you probably don't, because I don't understand it. I'm also a bit nervous because Martin's in the audience, and Martin does understand it better than I do, and I'm talking about it from supposedly with some authority. Martin, I'm especially keen for you to tell me if I get something wrong, as I undoubtedly will. But let's get started. So, can I just ask, who is using Scala in a job day to day at the moment? So probably about half, maybe a bit less than half. And I guess everybody else is keen to use Scala. And has anybody never used Scala? Good. Okay. So you've all at least had some exposure. So we can write things like this in Scala. We can you all see my pointer here? Yeah. So we can write things like this: val value equals hello. And I've left a gap here deliberately, because the compiler will work out that that is meant to be a string. You don't have to specify a string. It will put the type in there for you. So that is type inference working. What if I write this? If I have a list of left of 1, so 1 is an integer, and right of 2, what is the type of list here? Well, the compiler will automatically work out that even though you've not mentioned either anywhere, it works out that the common supertype of left and right is either, and therefore this is a list of either int or string. So that should all be good. What happens if I write this? I've specified the type here. What will the compiler infer? So I've not mentioned exception directly, but I've mentioned runtime exception. I've not mentioned either, but I've mentioned right here. And the compiler is able to work out that this is a right of an exception type, not a runtime exception, so it's not using this It's not using this value here to work out what the type is. It's using this expected return type, this type we've declared in here. So that's doing something different from the previous example. OK, that's when it works well. Who's experienced times when type inference doesn't do what you expect it to do? So there's a big waving hand from Martin here. It's all Adrian's fault, right? OK, so I want you to shout out with answers here. What type goes in here? If you've got this is an integer. This is a float, 1.0f. Any guesses as to what type gets inferred?
Float.
Float, correct. So what's wrong with that? This number is too big for a float. So the last two digits, I think, lose precision, and it ends up as something like 1, 2, 3, 4, 5, 6, 7, 4, 9.0 float. So we lose the some type or some value information there because the type that's chosen isn't as accurately representing that as it could. Here's another one. This looks similar. We've got a list that contains some integers and a double. And we're going to put a 0, another integer, in front of that. What type will be inferred here? Any val? Yeah, thanks, Martin. I'm glad you're aware of it. So, yes, we get any val. One of the least useful types there is, at least as an inferred type. We generally don't want any val there. So this is actually flowed onto two lines. We've got a big gap here that something will go into. Now, I actually lied a little bit on the previous slide. This is very similar to an example on the last one, where we had left of an int and right of 2. And I said that infers either of int or string. The lie was that it actually infers product with serializable with either of int and string. And this is correct, actually. There are good reasons why this is the inferred type, but generally that's not useful. That's not what we want to have inferred. And in order to get around that, we would need to explicitly specify that this is an either type.
But that's the fault of either, no?
That's the fault of either, yeah. What we could do is redefine either to inherit from product and serializable. And then in that expression there, they would be redundant. And the type that would be inferred would be either. So that would be the solution. And that's probably something that should be done. And in general, if you're working with ADTs and you have some case classes inheriting from a trait, you probably want to do that. What have we got next? OK, this is quite a simple one. You've got a variable, not a val, a var. So we're likely to want to change this later. This will infer the type sum of int, not option. So given that we've specified the value sum of 42, we probably want to have the possibility of changing that to none later. Otherwise, we'd just use 42. But none is not an option. Excuse the pun. None is not an option here. It infers sum. So we have to explicitly, if we want this to do something useful, we have to explicitly say var x colon option of int. Right, here's a good one. Any guesses as to what this comes out as? Shall I show you? Well, OK, I've not. The gap isn't big enough to show the type, so I'll show you what happens. So here's a REFL. Can you all read this? Is it big enough? It doesn't matter if it's not, because the result is this. So there we are. The type that gets inferred is an enormous structural type, which is correct in some sense, I think. But I think actually, Martin, am I right in saying that the type that's inferred is infinitely recursive in the structural? Sorry.
This one I'm not sure. It could be. It's very, very large.
Yeah. So this is actually fixed in Scala 2.11. Before I gave this talk the first time, I actually sat down to dinner with Martin the night before, and I said, why does it do this? I don't know if you remember. And I got out my computer and I said, here's the console. I typed it in, pressed enter, and it gave like a decent answer. So I was like, what's going on? I'm going to use this in my talk tomorrow. Problem was I'd used Scala 2.11, which fixes it, and the problem existed in Scala 2.10. But Martin said, but wait. And Martin got his laptop out and hacked around a bit. And said, you can actually do it in 2.11 with a different type. So this kind of problem is not completely fixed. It's a consequence of the complexity of the class hierarchy for collections that we end up with this ridiculous type.
Just to go back to my talk, that's what we need union types for. So to avoid this.
Yeah. So one more, and then I'll start explaining some of this, a little bit of this. Here's another one, quite similar, but we have a list of two companion objects, vector and list. Any guesses as to what this comes back with? Let me show you. So list of vector and list. So it's another big error, but this time it's a compile error. So how is that possible? How can it be that we haven't managed to get a type for this list of vector and list? I mean, you could always have a list of, we can specify explicitly any. That's fine. So why can't the compiler infer that? Well, this is a bug. This is the compiler looking at those two companion objects and thinking, the best common supertype for those two is this. It comes up with a type. And then it tries to use that type and finds it's wrong. So you get a compile error. So the compiler is sort of generating its own error. So this is type inference going on. I notice Martin's now left the building, so so I can relax a bit. But it means I won't get any help. So type inference is happening all the time. In an expression, in most expressions you write, there will be a number of types involved. Sometimes you see them. So in a polymorphic method call, that there is often a type parameter that's involved, and that type is very often inferred. So the question is, what would influence that type parameter? So one thing is the parameters that get applied to the type. So you call a method, a polymorphic method with a couple of values. The types of those values can influence what type is inferred for the expression. I'll show you examples of this in a bit. The expected return type can have an influence as well. So if we specify what, or if it's clear to the compiler what type is expected in a certain place, that can change the inference on a method or an expression that gets placed, put in that place when you call it. This one's maybe less obvious. If your expression is pulling in an implicit, and there's only one possible implicit value that will apply to that method, that is something which can change the way your method is evaluated. So it can influence the type. And finally, maybe this is quite obvious, if you explicitly specify the type in your code, so for example, when I created that list with any, that explicit specification of the any type for my list in the example in the REPL, that will override anything else, and that will strongly, absolutely in fact, influence the type. So I'm going to look at each of these. I'm going to give some examples based on the examples I'll give will use the exception type hierarchy, because I think everybody who's familiar with Scala, and even people familiar with Java, will understand the type hierarchy. I've put it into the song here. I'm not going to sing it, but we have at the bottom the nothing type, and at the top we have the any type, and then everything else fits in between. So the nothing type is a subtype of null pointer exception type, null pointer is a subtype of runtime exception, and so on. The lyrics are available on my website. You can sing it at home later. So let's have a look at the parameters you apply to a method affecting it. We have def foo. I've only got 26 minutes left. OK. we might skip a little bit at the end. We have a method, def foo. I'm not going to say what it does, but it takes a parameter of type t. Now, this t is the same t that we specify here. Now, this should very clearly, because we've specified an exception value here, the type that gets inferred will be exception. That is the same t. What about this one, where we have two type parameters, both of which... Sorry, we have one type parameter with two value parameters, both have the same type. And we give it two different things, exception and error. Well, in this particular case, it will find the best type it can that will satisfy all of those parameters. So that happens to be throwable. Throwable is the best common supertype of both error and exception. Is that all okay so far? So this is what we call the least upper bound, or the lub. Who's heard of lubs? Not many. Okay. So least upper bound is a general concept in maths, but it's used in a type system here to find the type that is most appropriate for a particular expression. So I don't know if you can read this. This says nothing. I'm using color coding here, and if it's a sort of bright, hot, glowing white color, that means it's a bottom type, such as nothing, or a lower type. If it is a dark, cold red color, then that is a top type. So we know that everything, all our types in the whole world are subtypes of any. And nothing is a subtype of everything. So everything is fitting between these two types. And I think I've got a diagram of this. Can everyone see this? No? That's right. This is it's actually an old diagram, but so not only is it too small to see, it is also incorrect. But the two do cancel each other out a little bit. At the top we have the any type, as you can obviously see there. And at the bottom we have the nothing type. And each of these each of these boxes is a type that fits in between, such as ints and the collections. And these arrows represent inheritance. It's kind of deliberate that it's so small, because I don't want you to focus on the details. But the fact is there is a single type at the top, a single type at the bottom, and everything else fits in between. So, least upper bounds. What I want to do is come up with... I'm nervous about calling it an algorithm, because the algorithm for doing it is so horrendously complicated that it's near enough impossible to fit into a single talk. So I'm going to call this just a recipe for finding the least upper bound. So given two types we're trying to find the lub for, what we want to do, first of all, is look at all of their supertypes. So maybe it's left and right. We look at all of the supertypes of left and right, and find the intersection, the common parts of all those supertypes. There may be type parameters that are involved, and we're going to say, well, for now, this is too complicated, we will ignore them. I'll work for an example of this recipe in a second. Any supertypes that are implied anyway, so if we have in our intersection we have both either and any, well, either implies any, so we don't need to include any, so we'll just remove that. And what we're left with, the intersection of those types, is the least upper bound for that particular pair or multiple set of types. So I'll show you this. We write the intersection using with, but I'll demonstrate this right now. So least upper bounds. So we've got list of right and left. Okay? Now, for each of those, we can say, well, the supertypes of right, including the type itself, has right, either, product and serializable I showed you before, any ref, and any. And if you look at left, it's very similar. The only thing that differs is the left type there. So remember, the next step was find the intersection of these. So right and left only appear on once on each side. So this is the set of types that are left, that remain, should I say. And if we remove the redundant supertypes, so any and any ref are implied anyway, we can get rid of them. So we're left with either, product, and serializable. And this is why we end up with either with product with serializable as the inferred type when we compare left, when we put left and right together in a list. So this is how that result comes about. Does that make some sense? Yeah. Oh, that's a confident yes. I must be doing something right. Okay. Here are two methods which are slightly different. They're different because the first one has two parameters in the same block, and the second one has two separate blocks. Otherwise, they're pretty much the same. The implementations we're not going to worry about for now. Now, if I were to write function 2, this is the two-parameter block version, and I wrote right of 1, and then in the next block, notice there's a gap there, suspicious-looking gap. The next one I wrote left of 2. This will not compile. Now, the reason is, what the compiler says is, well, I'm going to type check for this first block, and I'm going to try and work out what t is. So it looks at the first block, and you've given it a right. And it says, OK, well, that's obviously the inferred type of t is right. Great, let's move on to the next block. And it looks at the second block, and it sees you've put a left in there. Now, left is not a right. It's very different from a right. So this is a type error, and it will say expected right found left. We can fix this by specifying that this should actually not be right, but the supertype of right. In fact, we want it to be either of int and int. And then t will be inferred to be either of int and int, and therefore this will then compile. Now this is quite ugly. So if you were designing a library with a method like this, you'd probably want to go for the FN1 version rather than the FN2 version. But here's a different case. In this one, we've got two parameter blocks again, and we have a parameter there which takes a t, and then we've got another parameter block which has t as part of a lambda. Now, what this does is it fixes the t after it's seen the first parameter. So you can call this with, for example, 42 as a string. And then the function here knows, or the compiler knows that the function here is not from some unknown t to string. It knows that it's from string to string. So it can therefore know, without at the call site telling us that this is a lambda from string to string, it knows that this is the string concatenation operator. It knows that this, even though this is an integer here, that it is being converted to a string and appended to the end. So if you mapped this over the 42, it would come out as 421. Now the thing to note here is that I haven't specified, or this lambda by itself looks identical to the one you would get if you called it with an integer here. It's only by virtue of the type being fixed, having reached the end of that first parameter block, that we're able to know the type for the parameter for the second block. And in general, Scala is unable to determine a parameter type for a lambda. It's a very difficult problem. It's not Scala's fault. It's unsolved. Okay. So when I was researching this topic, because I thought the best way to learn about type inference was to propose a talk on it. So I proposed a talk, this talk, for the Scala Exchange in London at the end of last year, and it was going okay, but there were still some things I didn't really understand. So I thought, well, maybe I could look up some papers on type inference, or try and find some resources online, type inference in Scala. That didn't work. You'll find it very hard to find even any blogs or anything clear on the internet that describes accurately how Scala's type system works. So instead, I got a plane to Switzerland, and I took Adrian Moores out to lunch. Adrian wrote the type the type system in Scala, or most of it. And I said, Adrian, look, just tell me how it works. And he said, well, okay, think about it as a constraint system. Every step of the way, the compiler is looking at some constraints on your types, and it's trying to fit types to those constraints. So it evaluates an expression, and it sort of pulls in features or type bounds, information it has available to it from different places. So the time, I've just noticed the time says 25 minutes now, and it said 26 before. That was more than a minute ago, wasn't it? Never mind. I've been granted more time. Thank you, whoever did that. Sorry for the distraction. Different features get pulled into the to the constraint system, and as it progresses, it learns more and more about the types. And all it's doing is just solving for a set of constraints that are available to the compiler at each step. A step might be at the end of the first parameter block, at the end of the second parameter block, after implicit search. And consequently, reasons why type inference might fail are because the system is under-constrained, so there aren't enough constraints on the type. The type is too flexible, and the compiler can't work with it. Or it's over-constrained. There are two conflicting constraints on that type that mean the Scala compiler can't work it out. In the under-constrained example, you can often fix it with a type ascription. You put colon and some type, or you write the type explicitly in a parameter block, in a type parameter block. But Adrian persuaded me to think of it as a constraint system, and constraints are being added as we progress through type checking. So I'm going to show you a practical example of the next thing in my. You remember my list from earlier of the things that will influence type inference. Implicits. So I said if there's a unique implicit, that can influence the type for a particular expression. So what we might like to write sometimes is a method which has a default type. We can't do this in Scala. This is not valid Scala code. We can't say, in the same way that we can with the value, that we're going to default to string if it's not specified. But we would like to be able to do that. And actually we can, but the syntax is a little bit more verbose. Now the way to do it is ensure that we have one single unique implicit that has the highest priority, so it's going to be found by implicit search first, that will be pulled in if the compiler finds no better reason for choosing a particular type. Let me show you this. So we're going to add an implicit parameter here, and the type of this implicit parameter is t defaults to string. Now that is a type I created. If you follow me on Twitter, @propensive, my last tweet or 2 tweets ago, I gave you a link to a gist. You can check that afterwards. That shows you the implementation of this. But in practice, we can write code like this. And if we write foo of, I don't know, apple, we've specified that type. We are giving the compiler a very good reason to choose apple rather than some default. So in that case, we get an apple back. All we're doing is returning null and casting the null to the appropriate type. But foo of apple will give us an apple. Fine. But if we call foo without a specified type, it will default to string. And the reason is that because we haven't specified the type, there is no constraint there. So the compiler then looks at the constraints inferred from the implicit, and it's not even really magic, but it is a little bit complex, so I'm not going to describe it in detail, but by virtue of this type here, we're demanding that implicit, it will infer that the type is string rather than anything else. So I'd suggest look at the gist. It's on my Twitter account @propensive, and it's not it's complicated, but not that complicated. It's about 10 lines of code. Right, sometimes, well, actually, the first question. When you're writing Scala code, do you find sometimes that you have type parameters you want to specify explicitly and other times where you want them to be inferred? Yeah, sometimes? No? So at least one person has this requirement. But it's kind of inconvenient that you either have to specify all of the parameters in a block or none of them. If you specify none of them, the compiler will do its best to infer them all. But you can't just say, well, infer all of them, but the first one, I want the first one to be string. Now, we can actually get this to work by breaking down the application of the method, the parameters to the method, into two steps. So if we had some action, it has two parameters. Now, I want one of these to be inferred. I want one of them to be specified. This is going to take some type class which is typed on the S type. So let me show you how you rewrite this. First of all, we define a class with an apply method. Now the S moves to the class, so we're splitting this S and T up. The S moves outside of the method to the class, and the T moves to an apply method. And the parameters as defined for that method look very similar. It's pretty much the same as it was before. And we also redefine action to now take a single parameter, S. That's the one we want to specify. T is the one we want to have inferred. And we change the definition of that to create a new unapplied. And that means that when you call action string and then 42, the 42 is an int. The int will determine what T is because of that there. But we haven't had to specify int. So previously we would have had to say action string comma int 42. Now we can have the int inferred and string the string we can specify, and the string is what determines this type class here. So maybe this is a complex example to be giving quickly on one slide, but it's useful in many places if you find yourself needing to do that. So check my Twitter feed later for I'll include a link to the slides here so you can have a look at that. Right, so this is quite a big topic, subtyping, and it's really fundamental to how Scala infers types. So first of all, I'm kind of going to give an overview of what subtyping is and what it means for something to be a subtype of something else. So in Scala and in Java, typing is nominal, so it's based on the name of the thing. So if I've got a class B which extends from class A, by virtue of me saying B extends from class A, it does. So something is type B, and by virtue of that definition of B extending A, we know that B is a subtype of A, provided it is structurally sound. The compiler will stop us if we try and do something that simply won't work. So structurally sound, what does that mean? So B can be a subtype of A if we can safely substitute a B in place of an A. So if something is a subtype by virtue of it being a suitable substitute, and maintaining various invariants we want to keep. B can be a subtype of A if all the methods of B have the same capabilities as A. Now that's a very vague, it's very deliberately a vague statement. So what does it mean to have the same capabilities? Well, all of the methods in that class definition must accept as parameters and return compatible types. They don't have to be identical types. They can be refined or widened depending on whether they're parameters or return types. But they must be compatible. And fundamentally, if B is to be a suitable substitute for A, B must accept every argument value that A's equivalent method could accept. And likewise, B's method must return some value that A's method could return. It doesn't have to be, well, it can't be every, but there's a subtle distinction between every and some here, which is a sort of general theme running through type theory of the duality of the well, the whole duality of the system. And this is the same. This is kind of the same thing we have with covariance and contravariance. So who understands covariance and contravariance? Really? I'm impressed. This is good. No, you don't. Well, maybe you do, but it's quite complicated. We'll see some examples in a bit. I don't understand it, but when I was chatting to Adrian about it, remember this is the guy who wrote most of the type system. He said, "Yeah, I just change pluses and minuses around until it all compiles." And that approach isn't necessarily wrong, because it's very easy to change a plus to a minus, and the compiler does do the checks for you. So why not just get the compiler to help you? It's not unreasonable. But let's take an example with, we've got two case classes, co and contra, which co has a covariant parameter, contra has a contravariant parameter. Contra will always be in turquoise, co will be in purple. So we can say that if we've got two types, super, which is a superclass of sub, and we wrap them in a covariant type, then that superclass relationship will be maintained. It'll be the same whether they're wrapped or not. And the thing with contravariant things is that arrow reverses. So contra of a supertype is a subtype of contra of the type sub. So this is backwards, but that has its uses. And we can nest these deeper if we like. So co of super is a superclass of co of sub. And if we had contra of super, that is a superclass of contra of sub, because we reverse and we reverse back again. And if you mix them up, you sort of I'm not going to read these out, but these lines are statements of fact. You can trace them carefully if you like. Basically, all we need to do is multiply the pluses and minuses on the way to the type we're considering to know whether that type in there is covariant or contravariant with respect to the whole type. Okay, so there's a few people nodding, so I'm not completely losing everyone. We also have invariance in Scala. Now, that is to say that if you have a type that's not covariant, we haven't made it covariant or contravariant, then it is invariant. It does not change with respect to the wrapped type does not change with respect to the inner side. So ordering, the type class ordering, is invariant. That's one example. So if again we've got sub is a subtype of super, then despite that relationship between those two, sub and super, we can't say there's the same relationship between ordering of sub and ordering of super. They are different types. There is no relative super or subtype between them. What example have I got here? So if we take exception and throwable, even though throwable and exception are related, ordering of those things are unrelated. But there is one additional thing to note. If our foo type is a subtype of bar, and they both have the same type parameter, they're both typed on with the parameter t, then we can say that foo of int is a subtype of bar of int, but only because this type is identical, both sides. So this is the recipe I showed you before. Now remember, this doesn't work for type parameters. But we've now learned about covariance and contravariance. So let's see if we can improve that recipe to deal with those cases as well. So trying to find the lub with type parameters. So first of all, we go through the process as we did before. And I'm going to go through this quite quickly, first of all because I've got not that much time left, and also because it's going to be too long to explain so everybody understands. So I will quickly introduce you to a couple of ideas that are relevant when you're trying to work this out. So we find the lub of the main type, as we did before with that previous recipe. And then for each type parameter that is involved in those types we're finding the lub for, we trace how that type relates to its supertypes, how that type parameter t, or maybe we know that it's int, relates to, fits into the inheritance hierarchy. And we look at the variance on that type. So in the case where it's covariance, we then apply this same recipe to the covariant type. So you basically recurse on that recipe for every type parameter. And there might be several nested recursions to get that to work out the correct type. If it's contravariant, the lub is not what we want. We want the dual of that. We want the greatest lower bound, not the least upper bound. And this is basically, this is actually simpler. It's the set of types. Sorry, well, I'm going to read this out. The GLB, the greatest lower bound, is the set of types of a set of types, is the intersection type of those types. So we just get the types and we with them together, A with B with C. And again, we recurse on the nested parameters. So by all means, go back and read this later and spend longer trying to understand it. It's not that easy, and I struggle with it. But you can actually develop an intuition as to what types will be inferred in those cases. So the last factor, which might be relevant in evaluating the expression, is the return type. So I've got two methods here: ordify, listify. I don't know what they do, but one of them returns an ordering, and one of them returns a list. Otherwise, they've got a rather boring lambda here. The parameter t. Remember I said before that Scala can't work out a type t just by writing a lambda. It can't infer from a lambda literal what parameter types will be accepted. So this type needs to be known before Scala will accept this. So if we were to write we specify that this return type is ordering of int, and we write ordify underscore to int. We haven't specified the type here. Now this should be on a separate line. Sorry about that. If we had a different, if we expected a list here and we used listify, remember these two probably look very similar. One's using ordering, one's using list. So you might expect these either both to work or one to work and the other not to work. What happens? Well, as it turns out, one of them will work and one of them won't. Now, the difference is in the definition of ordering and the definition of list. That's the only place where they differ. List is covariant in T. This is the key thing. This is why if you have this here, oops, sorry. If you try and call listify on I'm struggling here. If you try and call listify and give it a lambda, we are not able, even though we know the return type, we're not able to work out that this parameter here, it goes from int to any. The compiler does not know this. It can't work it out. And you might think, why can't it work it out? Now, the problem is that it's covariant, whereas ordering is invariant. So in the case of ordering, that's the case that works. We know that that t in ordering, the t in the return type, which was int, is the same t in the parameter because it's invariant. There is no change that does not vary with the type. So t is exactly t. Now, in the case of list, this is going to be the most difficult statement to understand in the whole presentation. Now, you've had some difficult ones already. This one will be harder. So why don't we know that the expected return, why can't we work it out from the expected return type of list of t? So what we know that we've got a t, we know what the expected return type is, t, and we know that the t in the expression is some supertype of that t. Well, no, sorry, it's some supertype of something which is a subtype of t. So this is variable in this direction, and this one is some supertype of that other type. So actually, it is completely, I was going this way, wasn't I? So it is completely variant in both directions. So it could be anything from nothing all the way up to any. So essentially, we have no bounds on that type. It is unknown. So this is not the compiler being stupid about inferring the parameter type. The compiler just can't do it. And you can come up with counterexamples as to why if you work hard enough. But yeah, I'm going to read it out again. We only know that the actual t for the expression is a supertype of something which is a subtype of the expected return type. Got it? No. That's fine. Yeah, we know nothing about it, and our system is under-constrained, and we can't work with it. So in the general case, we can only use return types which have opposing variants to a type we're trying to infer from that expected type. So I'm pretty short on time. Can we go over by 5 minutes? No one said no, so I will. So for example, in this example here, we've got a contravariant. So return types are contravariant. So we can work backwards that, sorry, return types are covariant, but we have contra being returned here, which means that this t is contravariant in this expression. Parameter types are contravariant, but the parameter of a function is contravariant. So two contravariants mean that this thing I've got selected at the moment is covariant. And it's so this is also covariant. And because this is covariant and this one is contravariant, we can successfully infer this type. Try it at home later. Likewise, well, this is an example. We can expect contra of int, and this will be safely, the type here will be safely inferred. If we do the reverse, this becomes co, this becomes contra. This will also work. So we can do the same thing there with the dual case. But this will not be inferred, so I've changed the method name. We have to explicitly specify the type here of the lambda if we want this to work, because these are not opposing types. So back to the list. I'm going to give these in order now, because there is a priority as to how these are checked. So what the compiler will do first, it will say, have you explicitly specified the type in your expression? That will override anything else if you have. Failing that, it will look at whether the parameters are helping to infer the type. They will take priority over anything other than an explicitly specified type. Then it will look for the existence of a unique implicit. If there's only one implicit that satisfies the expression, then that will contribute to the type. And finally, if none of those are relevant to your expression, only then will the compiler look at the expected return type. So I think a lot of people feel that the expected return type isn't actually useful, and in many cases it's not. Because if there's anything with higher priority that overrides it, parameters, implicits, or explicitly specifying the type, then the expected return type will be ignored. So you kind of have to play a game. You have to make sure that you're designing your APIs such that your types are inferred by the right different elements of the expression. So we can make sure that if nothing else beats your expected return type, then we can use that. So that means no unique implicits that can affect it, no parameters mentioning that type in the expression. Likewise, if you want to take advantage of the using an implicit to determine the expression type, make sure you have a unique one. If there's more than one possibility for a particular expression, then the compiler doesn't know what to do. It needs a way of disambiguating. And then this is the point I made in the previous slide. And we can have different type parameters in an expression, which are each inferred by different means. So these different ways of inferring the type work together, but they're not related to each other. They're orthogonal. Now, who's familiar with can build from in the collections library? Nobody. Martin came back into the room just because I started talking about can build from. So yeah, I'm not going to talk much about can build from, except to say that it does take advantage of this feature in that it has type parameters in the can build from type, which I think I've got a slide on this. Can build from. There is a definition of can build from. 2 contravariant parameters, one covariant. And what it does, it's a type class. It's a way of building a new collection from an existing one. So the from type, that is the sort of elements within that particular collection. And this is the type we're going to. Now the to type, that type is used to essentially pull an expected return type back through the expression. So if you chain, for example, in a for comprehension, if you chain many of these together, the expected type of the entire for comprehension, that expected type can be pulled backwards through these types to determine which implicits are resolved along the way. And it's quite, the mechanism is quite complicated, but it's using the fact that the to type is not referred to anywhere apart from in the return type, the expected return type, that we can do this. And map and flat map, as commonly used in the collections library, both refer to this. And use this as a way of quite nicely, I think. It's maybe much undervalued in the collections library. It provides a way of using the expected return type to more efficiently, to more succinctly in terms of the code. You write less code to generate a resultant collection from a series of maps or flat maps or other operations on that type. So, a while ago, I tweeted this. Breakouts, let the party start. And I said, anyone in the intersection of people who understands both references, there are 2 references in there, please retweet this because you're special. Does anyone understand any of the references in here? I'm yet to find a single person who knows what I'm talking about. I gave this talk in Boston for any Scala, and Paul Phillips was in the audience, and he thought he knew. He knew one of the references. So breakout is quite a cool but little understood feature in the collections library that allows you to avoid the expected return type, changing the way the expression is evaluated. That's complicated, and I'm going to direct you somewhere else to look at that. This is also, I believe, a Miley Cyrus song, which is apparent if you search for Breakout. You try and search on Google for Breakout. You don't get Scala resources, you get Miley Cyrus. So you'll notice that I've asked people, I've invited people to retweet back in October, and nobody has retweeted this. No, the intersection of people who listen to Miley Cyrus and who understand Breakout in Scala is the empty set, which I think is probably a good thing. So the one thing to say about Breakout is if you're interested, look at Stack Overflow. You can search Stack Overflow for Breakout without any Miley Cyrus references. And Danielle Sobral has written a very comprehensive and a very clear, quite long answer about how that works. And it's very, very useful. I'm coming towards the end. There are a few things I've overlooked. There are many things I've overlooked. Overloading can mess up type inference. The compiler has some difficulty resolving types if there are overloads of a method. Weak conformance. We actually saw this at the beginning when our integer and float types were coerced into a float. This is sort of a bit like an artificial inheritance hierarchy placed on primitives, but there is no such hierarchy, so it's sort of added on. And it's useful most of the time, and occasionally it'll bite you. Path-dependent types is a whole other complex area. Is anyone familiar with F-bounded polymorphism? It's, yeah, there's a couple of people. It's sort of a trick for avoiding instances where you feel like you have a type that needs to be both covariant and contravariant at the same time, which is impossible. So you can use a thing called F-bounded polymorphism. That's searchable. There's a good talk by Marconi Lana, which should be available on YouTube somewhere, that talks about that. And the difference between type parameters and type members. These are reasonably interchangeable, but there are, in the Scala syntax, for example, there are biases towards always specifying a type parameter. I mean, if you specify a type, there is a gap where you need to specify a type for the parameter. Whereas with a member, you can very easily forget to specify what that member is in defining the type. So the Scala syntax is biased to sort of lose type members when you're specifying a type, whereas in the case of type parameters, it's biased towards forcing you to specify that. But in terms of the theory behind them, they're largely very similar, and Dotty unifies the two, so that's sort of further evidence that they are largely interchangeable. That is all I've got. Thank you.
I think we can demystify lunch now.
Yeah, sounds like a good idea.
If you have a question, he's around. So.
Yeah, come and find me and ask me questions. I won't promise to know the answers, but I might be able to point you in the right direction. Also,
one thing: the room is going to be split in two, so just so you know, you cannot go.
Can I just say one thing before you go to lunch? I'm going to shamelessly promote a conference I'm running in England in September. We have it's called Scala World. It's happening on the 21st and 22nd of September. And I've got a really cool lineup of speakers here. Sebastian, who was working on Scala.js, which was mentioned earlier. Julian, who works on the IDE. Matthias from Spray. I'm really pleased Debashish Ghosh is coming from India. Runar, I don't know who this guy is, but Runar is giving a keynote. Heather is going to come and I don't know, she might talk about spores. Eugene is going to demonstrate Scala Meta. I don't know if you know Edwin Brady, who wrote Idris. He'll be talking about that. Daniel Spiewak is giving another keynote. Miles will be talking about Shapeless. And Adrian, who I mentioned a few times in my talk, will be... he's got, I think, quite a cool idea, which I'm hoping he will talk about. And lots of other people. It should be great fun. It's set in the countryside in England. We're going to do some mountain climbing, and we'll do some outdoor stuff, and there'll be great food, and it'll be a lot of fun. And I'd love to see as many of you there as possible. So that is Scala World. The URL is scala.world. Thanks. Sorry? Oh, sorry. Don't worry.